we've been working with solving triangles, but we've been limited to right triangles, solving right triangles, which is very limiting because most triangles are not right triangles. Most triangles are acute or obtuse, and the word we use to describe both of those in one group is oblique. Oblique triangles are triangles that are simply just not right triangles. Oh, yeah. So this is what we're going to be working with for today. Hold on. Science. There it is. Okay. So this is what we're going to have today. We're going to work with these oblique triangles and try to solve them and learn some methods of solving them. Now, there are two basic methods we're going to learn. There's a third method which is pretty obscure and doesn't get used very often. They're called law of sines, law of cosines, and law of tangents. Tangents is the one that's obscure and doesn't get used very much. Sines and cosines are very common. Law of sines is going to have something as we work through this chapter called an ambiguous case. What does ambiguous mean? If something's ambiguous, vocabulary test. Ambiguous. That's a big word. Come on, all you honors English and AP English people. What? Abnormal. Okay. Ambiguous, kind of vague. Hard to define. Things are unsure. If it's ambiguous, you're not really sure what's going on. And that's exactly what ambiguous case is describing. We'll get to that. Those are all things we'll see as we go through this first half of the chapter. So a lot of stuff to talk about here. Like I said, though, SOHCAHTOA is great, but it doesn't work in oblique triangles. So I'm going to kind of develop law of sines here for you. We're going to show you where law of sines comes from. If I given two angles of a triangle, and here I am, 64 and 24, that's fantastic. Finding a third angle would not be a problem, because we know the triangles always add up to 180 degrees. So right now we're at 88 degrees. This is 92 degrees. Orientation is off just a bit. So that's 92 degrees. How do we find the sides? Well, there's a method we could use. We could drop the altitude of that triangle in. So I'm going to drop in an altitude from angle B, call the point of intersection down here D. Wow, it's really off. It's going to drive me nuts. And now I've got right triangles, don't I? Fantastic. Now sine of 64 is opposite BD over hypotenuse, 10, in that right triangle. Right? So sine of 64 in this triangle is BD over 10. So BD we know is 10 times the sine of 64. That's not hard to figure out. Sine of 24 is BD in this triangle over here, BD over BC. So sine of 24, since BD is 10 sine 64, sine of 24 is 10 sine 64 over BC. Or rearranging that by dividing both sides by 10, I get sine 24 over 10 equals sine 64 over BC. Or if I go to the general case, I know the 24 degree angle was angle C, so sine of angle C over side C, the side opposite of C, is sine of angle B, or A, 64 over the side opposite of A, which is BC. So essentially what we've done is we set up a proportion. Sine of C over C equals the sine of A over A. And if I redid this, if I change it and said, okay, let's drop in the altitude from A or the altitude from C, I would also get equals sine B over B. And that is the law of sines. The law of sines is a proportion law. That this proportion always exists. Now, because of proportion, I can flip it. If I want to put the side lengths on top and the angles on bottom, I can do that. But notice it's not the angle over the side, it's the sine of the angle over the side. Equals the sine of the angle over the side equals the sine of the angle over the side. Not the angle measure itself, but the sine of the angle. So that angle could be in degrees or radians. It's fine. That's our law of sines that we're going to be working with. And it's pretty easy to remember. It's not a tough formula. Not bad at all. And you don't have to remember how it's derived. It's just kind of interesting to see where it comes from. For some people. Other people are like, yeah, really. The really geeky math people are like going, oh, that's cool. I like how that worked out. I wouldn't have thought about doing that. You don't have to identify yourselves. We use law of sines to solve an oblique triangle when we know two angles in one side. Obviously, it's not going to work in all situations because we won't have enough information in a lot of cases. But if I know two angles of the triangle and one side, law of sines can always be used. So angle, angle, side, or angle, side, angle, either way, I can use law of sines. Because if I know two angles, I know the third angle by triangle sum, right? So if ever the case I know two angles of a triangle, 25 and 92, that gives me 117. That leaves my other angle to be what, 63? Okay? And I can solve this triangle very easily using law of sines. I'll show you how. What I'm going to do is, this is side B, this is side A, and so I could set up my whole proportion. A over the sine of 25 equals B over the sine of angle B, which is 63, equals C over the sine of angle C, or C is 17, excuse me, over the sine of angle C, which is 92. Now, I can't solve a proportion that has two equal signs like that directly. I have to do it in pieces. Obviously, I have to use this as one of my ratios. I can't solve this pair with the A and the B. I couldn't do this by itself because I don't know A or B, do I? I'd have two variables. So that's not going to work. So instead, maybe I'll start here because they're next to each other. How do I solve a proportion? I cross multiply. Or actually, easier still, I'm just going to multiply both sides by the sine of 63. Here's a little trick that I do. Because this proportion can be written sine A over A equals sine B over B equals sine C over C, or I can flip them all, I just always make it so my unknown variables in the numerator, since I'm searching for sides are my unknowns, I'm going to make sure that my sides are on top. It just makes life a little easier when we're solving the proportion. Multiply both sides by sine 63, so B is 17 sine 63 over sine 92. And I just put that in my calculator. 17 sine 63, be sure to close the parentheses, divided by sine 92. And I get that side B is 15.2 approximately. Now I can't use Pythagorean theorem to solve for the third side because it's not a right triangle. Some people make that mistake, saying, oh, I got two sides, I can use Pythagorean theorem. Sorry, only for right triangles. I have to use law of sines again. But in that said, this time I'll use these two. Okay? I'm not going to use a 17 or 15.2 for two reasons. One, it's an approximation. And I don't want to use an approximation to find the next value if I don't have to. Second, I'm not sure it's correct 100%. I'm 99.9% sure, but I'm 100% sure of 17. So I was given that number. Unless you've copied down 17 wrong, which has happened on occasion. But I'm more sure of 17 than I am of A. So, again, I cross multiply or multiply both sides by sine 25, and I get A equals 17 sine 25 over sine 92. So 17 sine 25, close parentheses, divided by sine 92, close parentheses, 7.2 approximately. And my triangle inequality is still satisfied in that the shortest side is opposite the smallest angle, the medium side is opposite the medianest angle, the longest side is opposite the largest angle. It's still making sense. Yes?
Does C always have to be something special, like angle C? Because I know in the right triangle it always has to be...
No. No. A, B, and C can be anything at this point. Because they're oblique. It could be acute. This just happens that it was the largest angle this time. It says perfectly acceptable to flip it. I'm not sure why the fraction bars aren't showing up, but they should. So again, solving triangles, and you get lots of practice doing this today. Again, given two angles and a side, we want to find side B. In order to do that, I'm going to have to start by finding angle C. So the measure of angle C, here A is the largest angle, B is 110 and 35 is 145, so angle C is going to be what? 35 also. Gee, angle B and angle C are the same. What does that mean about side B and side C in this triangle? They also have to be the same. It's an isosceles triangle, isn't it? So facts from geometry pop back up into our heads sometimes, painful as they may be. But if two angles are the same in the triangle, then the sides opposite them are also congruent. All right, so it says find side B, so B over sine B equals, I could do A over sine A or C over sine C. I have side C and angle C, so I'll do C over sine C. When I put numbers in there, B over sine 35 equals C 17.2 over sine 35. Oh gosh, what's B going to be? Obviously, 17.2. If I wanted to find A, that would be A. We could also do A over here over sine 110. If I wanted to find A, I'd just solve that proportion. So 17.2 times sine 110 divided by sine 35. Law of sine seemed pretty straightforward to people. When we know two angles and a side, it is pretty straightforward. We have application problems for this. And here's where some of these problems that we did before, they were really hard, where we had to do the funny, set up systems of equations with mountains and stuff like that. Here's where law of sine comes in really handy. You're trying to determine the height of a mountain. From point A, the angle of elevation is 38 degrees. Okay? So I got some mountain over here. There it is. It's the Matterhorn. All right. From point A, the angle of elevation is 38 degrees. From point B, the same elevation of as A, the angle of elevation is now 41 degrees. Points A and B are 1,000 feet apart. Find the height of the mountain. Still got a right triangle here, but now my problem is a little bit easier. Because I can start, before I set up my SOHCAHTOA to find the height of the mountain, because I'm eventually going to have to do that. There's H. I can solve this side of this oblique triangle. Okay. Because I know this angle is 38 degrees. I know this side is 1,000 feet. What is this angle going to be right here? 139, yeah. Making this angle up here 3 degrees. So I know all 3 angles of that oblique triangle, don't I? And I know one side. So I can solve for this unknown side right here. And why do I want this one? Because this is going to be the hypotenuse of that right triangle I need, isn't it? That's going to be the hypotenuse. So I can use law of sine to sign this x over the sine of the side opposite. So x over sine 38 equals, now I want the 2 I know, 1,000 over sine 3. So 1,000 sine 38 close parentheses divided by sine 3. Somebody's going to, I say close parentheses every time I do that because somebody's going to forget to close their parentheses. And you're, instead of calculating 1,000 sine 38 over sine 3, you're going to calculate 1,000 sine 38 divided by sine 3. You're going to do that, which is completely different. All right? So be careful. Close those parentheses. I get that side is 11,763 feet, 64 rounded to the nearest 10. 763. So I know now this is 11,764, and now I could solve this green triangle using SOHCAHTOA. That should be sine. Sine of 41 is the height of the mountain over 11,764. So 11,764 sine of 41, 7,717 feet. And 18 feet rounded. Here's split. So now I've got the height of that mountain. That's a lot easier than the whole x minus h and setting up the system of equations, isn't it? So immediately law of sines takes something that was a problematic situation for us in story problems when we only had SOHCAHTOA and turns it into something that's pretty manageable. I mean, 2 calculations and we've got it. No systems of equations, no nothing weird like that. All right. Assignments. Oh dear. The school website's down, isn't it? I don't think I can. Well, I can find it. I'm just going to see if I can access it internally. We can still access internally. Okay, good. There we go. Excellent. So there we go. Hopefully not too scary for Halloween. And look, we're even done in plenty of time today. You have like 10 minutes of work time today. What are you going to do with yourselves? Be afraid. Be very afraid. Something is wrong here. Something is very, very wrong.